Wallis formula can also be used in integrals, which can be transformed into sine-cosine combination, such as one which has the pattern of a squared less x squared. Learn more about it here in integral calculus. The first example requires the definite integral of x cubed times the root of the quantity 9 minus x squared dx. The quantity inside the radical actually conforms with the pattern of a squared minus x squared, and its trigonometric pattern is x as sine of theta, which makes the example 3 sine of theta. The other parameters to be transformed are dx and the quantity inside the root. Use the triangle and identify the sides from the assumption. Saying that x is 3 sine of theta and theta is assumed as this corner of the triangle, x is at the opposite side, and the hypotenuse is 3. Hence, the last side is computed as the root of 9 minus x squared using Pythagorean theorem. A trick to use when transforming the side with radical is to use the constant side of the triangle instead of the variable. Thus, choose cosine of theta as the root of 9 minus x squared over 3, making the quantity with the radical equals to 3 cosine theta. The last parameter to look for is the derivative of x, which turns out as 3 cosine of theta d theta. The limits should also be transformed from x to theta, and it is done using x as equal to 3 sine of theta. Jumbling the terms, we get theta as arcsine of x over 3. From here, we can transform the lower limit of x equal to 0 from theta as arcsine of 0 over 3. Then theta is 0. For the upper limit, where x is 3, theta becomes arcsine of 3 over 3, or 1, where theta becomes pi over 2. With all components already transformed, substitute them back into the function to have the integral of the cube of 3 sine theta times 3 cosine theta as the transformation of the quantity in the radical. Then multiply dx, which is transformed as 3 cosine theta d theta. The integral is within the upper limit of pi over 2 and lower limit of 0. Having the transformed function, bring out the constant, which is computed as the cube of 3 times 3 and another 3, giving 243 placed outside the integrand. Then the trigo functions are sine cube theta with cosine squared of theta d theta. Now that a combination of sine and cosine is out with the preferred limits of pi over 2 and 0, use Wallis formula to integrate. That is, taking 243 times the double factorial of 3 less 1 times double factorial of 2 minus 1 all over the double factorial of 3 plus 2. Then alpha is considered as 1 because there is an odd-numbered exponent. Simplify the factorials and have 243 times 2 over 5 times 3, giving the final definite integral of the function as 32 and 2/5. Example 2 requires the integral of x raised to 4 over the root of 1 minus x squared times dx. The denominator has the pattern of a squared less x squared, so use the sine trigonometric substitution, where x is 1 times sine of theta. The parameter with the radical can be determined using a right triangle, where the opposite side of theta is x. The hypotenuse is 1, and the remaining side is root of 1 minus x squared. Cosine of theta is the root of 1 minus x squared over 1. So the quantity in the radical is cosine theta. Also, dx is the derivative of x, which is cosine theta d theta. Transform the limits in terms of theta as well. That's using x as sine theta, where theta is taken as arcsine of x. Start with the lower limit, x as 0. Theta becomes arcsine of 0, which is also 0. The upper limit, having x of 3, is transformed through theta as arcsine of 1, which makes the upper limit theta as pi over 2. Now plug all parameters of theta into the function and have the integral of sine theta raised to 4 over cosine theta times cosine theta d theta from pi over 2 to 0. Cancel out cosine theta to simplify the integral. With the reduced integral of sine theta raised to 4 d theta from pi over 2 to 0, this is a perfect form for Wallis formula, which is computed as the double factorial of 4 less 1 over double factorial of 4 times pi over 2. This is expanded as 3 times 1 over 4 times 2 multiplied by pi over 2. Simplify the terms to have the final definite integral of the function as 3 pi over 16. The next example looks for the antiderivative of the root of 9 minus x squared over x squared dx from 3 to 0. It is obvious that the numerator has the pattern a squared minus x squared. So work with the trigonometric substitution using x as a sine of theta, which is customized as 3 sine of theta for the example. The term with radical uses the right angle, where the opposite side of theta is x, and the hypotenuse is 3. So using Pythagorean theorem, the third side is the root of 9 minus x squared. Take cosine theta as the root of 9 minus x squared over 3, making the quantity with radical as 3 cosine of theta. Lastly, the derivative of x is 3 cosine theta d theta. With the transformation of the expression, do the same with the limits, using x as 3 sine of theta, where theta is determined as arcsine of x over 3. For the lower limit, where x is 0, theta is computed as arcsine of 0 over 3, which yields 0 for theta. The upper limit of 3 can be transformed as arcsine of 3 over 3, which makes theta as pi over 2. Now that everything has been transformed into theta, the function is taken as the integral of 3 cosine of theta over the square of 3 sine of theta multiplied by 3 cosine of theta d theta from pi over 2 to 0. From the function, simplify terms to have 9 cosine of theta squared over 9 sine of theta squared with d theta. 9's cancel out, leaving cosine squared over sine squared. With both functions as a square, we use Pythagorean identity to reduce terms. Take cosine squared theta as 1 minus sine squared of theta, and plug these into the numerator, after which the terms can be separated into the integral of the reciprocal of sine squared theta d theta minus the integral of sine squared theta over the same with d theta. By reciprocal identity and cancellation, the integrals turn into cosecant squared of theta d theta minus just d theta. By using trigonometric integration, we get negative cotangent of theta minus theta with limits from pi over 2 to 0. Since the integral did not turn out as combination of sine or cosine, Wallis formula is not applicable. Now, if the limits are plugged into the antiderivative, both cotangent of pi over 2 and 0 are undefined, resulting to no definite solution for the integral. The other example is the integral of x raised to 5 times the quantity of 1 minus x squared raised to 3 halves dx. To come up with the radical, we can rewrite the function into x raised to 5 times the cube of the root of 4 minus x squared. Then the quantity in the radical has the a squared minus x squared pattern. So with trigonometric substitution, x is assigned as a sine theta, which is taken as 2 sine of theta. The root is derived from the triangle, where the opposite of theta is x, and the hypotenuse is 2. The remaining side is solved as root of 4 minus x squared. Use cosine of theta as root of 4 minus x squared over 2. So the quantity with radical is 2 cosine of theta. Dx is also taken as twice of cosine theta, d theta. Transform the limits too, using the assigned x as 2 sine of theta. Theta is then computed as arcsine of x over 2. For the lower limit, x as 0, theta is arcsine of 0 over 2, giving theta as 0. The upper limit of x as 2 can be transformed as arcsine of 2 over 2, which becomes pi over 2. Substitute all parameters into the function and get the integral of 2 sine theta raised to 5 times 2 cosine theta raised to 3 times 2 cosine theta d theta. With the function totally transformed in terms of theta, bring out constants and combine functions to get 512 times the integral of sine theta raised to 5 with cosine of theta raised to 4 d theta, from pi over 2 to 0. Wallis formula fits the format, so the solution can turn out as 512 times the double factorial of 5 minus 1 times the double factorial of 4 minus 1 over the double factorial of 5 plus 4. Then everything is multiplied by 1, as the exponent of sine is odd. Continue with the solution with 512 times 4 times 2 with 3 times 1 over 9 times 7 times 5 times 3. So the final definite antiderivative for the function is 13 and 1 out of 315. Another example is the integral of the root of 4 minus 9w squared dw from 2/3 to 0. To use trigonometric substitution, the pattern of a squared minus x squared should be followed without any coefficient. So we need to eliminate 9, and that is done by dividing both terms by 9. Now the root has 4/9 minus w squared, exactly as the pattern of a squared minus x squared. From here on, use the trigonometric substitution of w as equal to a sine of theta, or for the example, w is 2/3 of sine theta. dw is also 2/3 of cosine theta d theta. The other parameter to transform requires a right triangle, with theta and x as its opposite side, 2/3 as the hypotenuse, and the remaining side as the root of 4/9 minus w squared. Cosine theta is the root of 4/9 minus w squared over 2/3. So the quantity of the root is 2/3 of cosine theta. Next is to transform the limits using w as 2/3 sine of theta. Theta is then arcsine of 3w over 2. For the lower limit of x is 0, theta is arcsine of 3 times 0 over 2, which is 0. The upper limit with x as 2/3 makes theta as arcsine of 3 times 2/3 over 2, giving theta as pi over 2. Place all parameters into the integral and have 2/3 of cosine theta times 2/3 cosine of theta d theta, simplified as 4/9 times the integral of cosine squared of theta from pi over 2 to 0. Use Wallis formula for cosine, then have 4/9 times the double factorial of 2 minus 1 over the double factorial of 2 times pi over 2, which eventually turns into pi over 9 after simplification.